Welcome to Linear Momentum Conservation Online Lab. If you're viewing this video, I'm either dead or the campus is closed to a coronavirus, or maybe both. Okay, linear momentum has the symbol P with an arrow on it. Momentum is the quantity of motion. How much stuff is moving? It's the mass of the object times the velocity. These arrows means they have vectors. They are vectors. Moving north with a momentum is not the same thing of having a momentum east or straight up. The units we'll be using in this lab for mass are kilograms. For velocity, they're meters per second. Now, Newton's second law says that the quantity of motion, the linear momentum of any system, will not change over time unless there is a net outside force that causes that quantity of motion, the momentum, to change. Now, this is true for an isolated particle. It could be in nuclear physics. It could be true for a collection of particles, each little piece or all the pieces. And it's even true in today's thrilling lab for two collections of particles, two gliders that collide. They're going to collide totally inelastically. This pin is going to go into this mushy stuff, and they're going to stick together and move together. Now, the fact that one glider hits another glider means that each individual glider's momentum will change. One gets bumped forward, one gets bumped back. However, the total collective momentum, system 1 plus system 2, will not change unless something outside causes it to change. So in the lab, walking over slowly, I have previously balanced the height of this track. There are wheels here, such that if there's any teeny bit of kinetic friction or air resistance, or downhill or uphill due to the table not being level, the gliders feel no net force. One way of checking is when it goes through, it takes the same amount of time. So it's not slowing down or speeding up. Another way is I placed them at the center and they didn't drift. And so as the glider system moves from here to here where we measure the time, and I'll be talking about that later. For those in Physics 100, we've already done this a couple of times. For physical science, this is new. The time won't change. Going back to our board, which has somehow timed out. So the initial momentum, Pi, is just the first glider times V initial. The second glider, the target one, is going to be held by your partner at rest, in this case me. Afterwards, the first and the second glider stick together in that total inelastic collision, and this whole train shares a common final velocity. And if the horizontal forces on the track are negligible, the initial momentum and the final momentum will be equal with an experimental error. Walking over to the side. So Newton's second law again says if the net outside force acting on your system, the collective system is the two gliders, is 0, the initial momentum equals the final, the change is there. So we've balanced air resistance, gravity, and friction, which were small imbalances, and so it should work pretty well. Okay, the nuts and bolts of how we do it. For those who are new to this glider system, we have a photo gate, an electric eye. When you go between the beam, you break it, you get to see a time. And a liquid crystal display, you can zero it. If you make sure these flags are perfectly straight, parallel this long edge to the track, the distance this thing travels through the beam is exactly 0.100 meters. So if you know the time it takes to break the beam, and you know the distance traveled, velocity is distance over time. It's not going to be miles per hour, it's going to be meters per second. To ascertain the mass is pretty simple. You put that on a balance, a scale, and it gives you that. You convert to kilograms. All right, taking a look at the data chart. What you have on the online version is some of them are filled in for examples, as well as having some sample calculations. But ultimately, there's going to be 3 collisions. Your version is different. Every collision, I'm going to vary the mass of each glider system The first collision won't have any extra chrome weights, which I'll be demonstrating. The second one will put 2 more on, the third one 4 more. And the starting velocity would have varied. I'd give it a different push each time. But for every collision, the second glider starts out at rest. For every collision, the first glider hits the second glider, and the two of them stay together, the same final velocity. So going back to the first page, this is what we're going to calculate. And how do we calculate it? We have this. The length of the flag over the time is the velocity. The length of the flag, if it's straight, is exactly 1/10 of a meter. We divide by the time it takes to cover that 1/10 of a meter, we get the velocity. The initial velocity is just the first mass times the initial velocity, which is this guy. Over here, we're having some problem with the subscripts. But the second mass isn't moving. The final velocity is just the same length of the flag going through the same gate. And that second time is going to be longer because the two masses are going to share the momentum, so they'll have a lower velocity. It's the total mass times the final. And we compare it with sample calculations in the in the web version, and you'll get to see it and it will make sense. So let's go over to a quickie demonstration, see if it works out. Walk slower for the camera. All right. I'm lining this up so it's dead center and straight and perpendicular. Normally you'd have your partners doing that. I've only done this 289,000 times, so it's not too bad. All right. And then you turn on the air like you don't care. Zero these things. Now this will work a lot better with a partner, but I'll give it the old community college try. Hold this at rest. When it gets close, I'll release it without being a spaz. You stick together, and then you read the final. And technically, we do it again because I had a second flag on it. That's all right. I've never made this video before. Give it a nice smooth run up. Measure the 2 times, and we're done. You would repeat this. You always know M1 has the flag by adding masses. So for the second collision, which is in your sample data, be adding another 100 grams or 1/10 of a kilogram. You re-zero the gates. Make sure it's not moving. Give it a nice smooth run up. And then boom. Measure the time. And you repeat it for the third collision. So I add another 100 grams on each side. For the camera to see. Zero this thing. Obviously my technique would be much slower and careful, but we have to keep these videos short. Give it a nice smooth run up, let go, and boom. You record the times. The time through the first gate is T1, the second gate is T2. The data is there, a sample calculation is there. You just do the other 3. Find the total momentum, find the percent difference, but the samples are well written. You shouldn't have a problem. If you do, email me, come to virtual office hours, send a letter, whatever. I'll help you. We're out.